Cool. Yeah, so I'm really overwhelmed today by all these talks, especially in machine learning. And I won't lie to you, I won't add anything on top of that. And also, we're not selling trucks to the US as well. But what I really want to talk about is graphs and streams, which are some different aspects of data processing and computation. And probably you've heard of them, but not in combination, I would say. I'm a PhD student at KTH. I'm working with Professor Seif Haridi. And many parts of our work have been committed to this system called Apache Flink. Probably you know it. It does streaming. And we're very excited about it. So what do we want to do? Let's start with the basics. We want to analyze data. And we want data that is basically complex, right? And by complex, I mean definitely not individual measurements from sensors, but something more deep, something with a structure, let's say, like human relationships. That's very complex. We also want to do this in large scale, and that's something that current technology allows us to do, and that's very inspiring because we can take billions of these complex events and run very, very large-scale analysis and extract some useful information. But a new aspect that is becoming more and more popular these days is to make everything fast, because it makes sense to answer questions fast today when we actually have these questions and not a week or a month after, right? But you might ask, okay, we want to do that, but why? Why do we want large-scale and complex and fast data analysis? Obviously, because now probably we can, but also because maybe we must answer some big, complex questions very fast. And by that, here is an example, like a fast forward, I would say, to the future. Probably you know Siri. It's an agent that you have probably in your iPhone or your laptop. It crawls your data, and probably you never use it. But let's say this is future Siri. This is Siri 9000. It can answer any question in the world, and it has access to all data. What would you ask? Yeah, you can ask for the best route to work if you go to work. That's something you can already do, right? Maybe you can do something more deep, like ask the best route to work. And by best, I mean the safest. And we know that self-driving cars will be very safe, probably safer than humans. So that's a good choice. And so that's something you need complex analysis to do. You might also want to throw a party and make some pizza for your friends. But in order to pick up the best recipe, you might need some very complex analysis. So let's say you need something that your friends didn't eat yesterday or the day before, and we hate kebab pizza. So definitely know that. That's something that requires complex analysis. And usually, I like philosophical questions, especially at night when I'm on bed. I think about philosophical things. And I would like to ask Siri, what is the possible way to reunite all data science in the world? Or maybe is it possible? This requires some very heavy computation. Is it a computational problem? I don't know. We'll see. But yeah. There are many systems out there. And this is a very, very complex problem. Actually, in fact, systems can actually analyze these things today and can extract useful information. But are these really the questions we want to answer in, let's say, 1,000 years from now? Are these really critical questions? Won't we have something more serious to deal with? Or maybe in, I don't know, yeah, these are first world problems. Let's say in 30,000 years from now. Maybe we won't exist, exactly. That's my point. So these are first Earth world problems, I would say, that we want to answer. But okay, let me get you back to today and to Earth. And by Earth, I mean, we can still do something useful with it. And I think big data analysis, fast analysis is very important because it might save our lives and our species maybe in the future. Let's say there's a very deadly virus. That's very probable to happen. A deadly virus that spreads all over Earth, and we have a handful of medics that can help, but we can't really throw the medics everywhere. We have to be very selective in order to save our species, not our lives. So what we would have to answer here is, here's a map. And we would like to basically find out which groups of people are the most risky to get this virus. Or maybe if things get really worse, which groups of people have not conducted this virus, and maybe we can send some aircrafts there, pick them up, and send them to a space station or something. So maybe that analysis might save us if we have these answers, let's say. Okay, now to the beef. We want to analyze data, but how do we do that? And this is the actual thing I want to talk about. We have 3 requirements. Large scale is solved by a paradigm called distributed programming. Complex analysis usually is handled by another paradigm called graph processing, and fast is dealt with a paradigm called streaming. And there are 3 paradigms that conceive data in different ways. So if we're talking about graphs, we want to think that everything's a graph, and maybe write applications based on graph information, connectivity information. When we do distributed systems, we want to think that there are many, there's not one. There are many graphs, many parts of the graph, many vertices, many edges. We have to think in a distributed way. And also, to make things worse, streaming requires us to think everything as a stream. So this is insane, right? And I can feel you. This is it's very hard to think of all these paradigms together and fit them together. But that's our job. But for now, let me get here in the beginning and say, how did graphs came up in the first place? There was a guy called Euler. He was a mathematician, and he had this first-world problem because we like solving first-world problems. They're more interesting and more fun, right? So basically, he was in this city, Schöneberg. I don't know how to pronounce it. Schöneberg. That was in Prussia. And probably he was traveling there, and he had 1 hour to see everything in the city because he would miss the plane. So he had basically to see everything once and not duplicate his routes, basically. So in the end, he had to cross all these bridges just once. Okay, that was a problem. And he started thinking about this, and then he got really depressed because he didn't find any solution. It was a very complex problem. But in the end, he said, if I put a dot here, an edge for every bridge, and connect those together, then suddenly the problem becomes very simple. And the essence is that graphs make complex problems very simple. And that's a good thing. Today, things have escalated, of course. When we talk about graphs, we talk about complex behaviors in social networks, more probably. And of course, we have more advanced machinery, so we can do parallel computation on this complex data. So that's what made distributed graph processing. And probably you know MapReduce. MapReduce is a paradigm, a programming paradigm, or a technique for actually processing data in parallel. Most of you know it, I guess, but the process is that. So we store the data in a distributed file system. Then we send some local computation to nodes. They do some local computation. When they are done, they shuffle the results, and then we do some final merging, let's say, and we store back to disk. The graph version of this, so if you combine distributed systems and graphs, works in a bit similar way. I would say it's a bit more efficient for graphs. So systems like Pregel and so far have come up with this type of architecture. So basically, first they load the graph into memory, and then they have this. They get stuck in a loop within this map function, okay, locally. And what they do is that they keep processing their local graphs, and they send some events. They shuffle some events around. These are the changes they want to apply. Let's say they send some messages. Then they repeat the process in a bulk synchronous way. One again and again and again. Okay, we're done. Until we have no messages. If we have no messages, then our computation is complete. It's a very simple way of processing graphs in parallel. I call it store, load, compute, or load, compute, store. Same thing. And basically, if you have a complex graph like this macaroni maze there, we might want to do some parallel computation. In this example, we want to actually identify isolated subgraphs, basically graphs that don't connect to each other. This is called connected components. And basically, in this example, we have 3 connected components. When we are doing this in parallel, we split this into rounds. So in the first round, every vertex has its ID, and it sends some messages. In this case, it sends its local ID. Then every vertex picks up these messages and changes its value to the minimum. And this magically, if we repeat this process magically, we end up with no messages and with the same value in all vertices in the same connected component. So we have actually solved connected components. We can isolate graphs. And that's very cool. This is something that all the systems you see there, and maybe more, can actually do very efficiently in a very large scale. And I highlight scale because the problem is they're not doing it fast. Every time you want to compute something, you have to load the whole graph in memory, all these nodes. This is very annoying because you have to recompute a lot of redundant graph computation every time you want to extract some information. This is not a good paradigm to solve critical problems. It's a good paradigm to solve complex and large-scale problems, but not fast. And that's where streaming came into place. To make everything fast and simple. So we have the real world, and the world has extract some events. We take these events and we push them directly into a data flow pipeline. That's the idea of streaming. We just process everything as it happens. Maybe we have some queue in between, but there's no much disk access. We just get the events and we do some local computation or parallel computation in a orchestrated cluster of tasks. But what makes this paradigm different is that we keep local information inside this process that we see there. So basically, we have to compute to extract the knowledge and keep it inside these local nodes. This makes things a bit more complex, maybe, but when it comes to complex processing. But in the end, we gain a lot of other things. We gain a lot of sub-second latency and high throughput. We can do this in a very fault-tolerant way. We don't need to care about failures. We have done some nice work on this part. Also, we can process late data. So this is a very sophisticated way of processing real-time data. But what about complex problems? So can we really combine complex, large-scale, and fast processing? The problem is that we cannot really fit graphs into local nodes. It's a lot of information. If we have the universe graph, for example, we can never do anything about it if we're using this paradigm. But the thing is, we don't need to, because the essence of the problem is not to store the graph, but to actually compute some information from the graph. So what we can do is that we can extract some summaries from our graphs and keep them inside these local nodes. And there's some very useful summaries already, like spanners, sparsifiers, and sketches that can be used to extract some computational information on the fly. Let's see now how we could do connect components in the streaming paradigm. So basically, in this case, we just process edges. These are edge additions. And we create our components on the fly. So this is a very simple summary. It's a data structure that you probably have learned in your bachelor's. It's called union find. So if you have a union find or some bitmap, let's say, that isolates sets, we can actually create this local summary about connect components. And we can have the current connect components of a very complex graph always in memory. That's very powerful because we end up having the answer already computed at any time we want it, right? And you might say this doesn't seem very distributed, right? This is very sequential. It is sequential, yeah, but it can be distributed, of course, because you might have a parallel stream of edges. You can partition your edges or your edge stream and process it on the fly in parallel machines. And in the end, when you have something like a window computation, something that triggers frequently, you can actually combine those summaries in a very lightweight way to produce your global property, which is in this case, connect components. Are there any systems in mind that can do that? Well, yeah, we have a system. It's called Jelly Stream. It's built on Apache Flink. And you can actually go and use it, even today if you want. It can do some nice things. There is also a version of the system for static graphs, but this version is for dynamic graphs. You can have a stream of additions of edges, and you can do in a single pass, extract in a single pass a lot of useful information. You can see here some examples of existing algorithms we have already implemented in the system. So you see triangle count. Triangle count is very useful if you do things like security and you want to detect fraud, to do fraud detection or things like that. There are many examples. I don't have time to explain you, but let's focus on connected components. We can isolate. Now we can isolate. We can find isolated groups of people, right? Very fast, in a large scale, in the Earth scale. That means that probably we solve our problem. We can save Earth, right? Save humans, I would say. And that's very nice. But we also have one problem left, so don't go to lunch yet. There's one problem left. We need to solve this. It's really stuck on my head. How can we know if we can reunite all data science in the world? They're split into different communities. How can we do that? Well, let's say Siri has the answer, but it takes a lot of time. So we need to actually help it, I guess. Let's see. It takes some time. Sorry about that. OK, so this is our solution. So basically, you can use JellyStream, our system, to do this. So you can get a graph stream of all check-ins in the world, right? You know which people are data scientists, and you can filter out the data scientists. That's very easy. It's like filter vertices. Vertices are people. This is a bipartite graph, by the way. So we have people and places. That's the only type of nodes that we have. And basically, whenever someone checks in, we get an event in our stream. So we filter out data scientists, and what we do is that we slice the stream every 10 minutes. So we get basically all updates that happened during the last 10 minutes. And then we apply functional neighbors, which is find pairs. So we can find people that are close by, data scientists that are close by, and then create pairs of those people, and then notify them. There's a data scientist next to you. So then we can probably reunite all of them. I don't know. Can we? One using Spark and the other using Flink? Yeah, but who knows? Oh, yeah, cool. All right. So what we're doing now is that we want to add one more dimension. We have fast, we have complex, and we have large scale. We want to add deep. And deep, by deep, I mean that we want to add iterative models on complex graph processing. This is our current work, and we also want to do some more complex things like system-related things like extracting, using larger scale state in your computation. So maybe you can probably in the future store the whole universe graph if this research succeeds. And also query the graph. That's very useful. You can do real-time queries on the current computation of the graph. This is very useful. So try it out, and if you want, you can follow me on Twitter, and my colleague Vasya, who we started this project together. Yeah, so if you have any questions, I can answer, maybe.
So let's first thank the speaker. And we have a couple of questions up here. A couple of them slightly larger than the third one. So I would actually say, perhaps you can give a short answer to the final question there, at least a little bit hint onto how do you balance the loads on irregular graphs?
Oh, yeah. I didn't expect this question. Yeah, so the system allows you to use different partitioning methods. If you have a large queue graph, you can probably do a different type of partitioning. We haven't worked very intensively on this part, but and you know this is streaming, so skew doesn't really matter so much because you don't have a full graph to process. Basically, you just process events as they happen. So it might happen that some partitions have more information to process, but if your parallelism is big enough, probably you can handle it. But yeah, this is something we haven't looked much in depth yet, and we are actively. Yeah. Some other people in our group worked on this, actually, yeah.
Okay, and those two first questions are very interesting. I think we should take them as discussion subjects for lunch.
They're open questions anyway. Yeah.
Yes, and then just to close with a final question for you then. Should I use Spark or Flink or just IPython?
I would say if you want to do interactive analytics, Spark is more user-friendly. If you want to do more complex pipelines, probably Flink has a bigger advantage.
All right.
That's my opinion.
Thank you very much.